Anyway, okay. I'm recording now, and I'm going to share my screen. We're going back to what we were doing. Yeah. I think if I just share this one thing, it'll be better. Okay. Okay, so remember this, we were looking at this. See if you can figure out what the coordinate vector for our polynomial up here, P, our vector, is on this basis here, this A basis. Wow, it's not four. No, I'm gonna mute myself. My computer keeps making the annoyed sound.
A C value can be in terms of X, right?
Sorry, what do you mean in terms of x?
Like saying C5 is 3x or something.
No, it'd be coefficients of x.
Hmm.
Yeah.
Okay.
Yeah. Van? Van? How's it going out there?
I'm stuck.
Stuck. Okay. How about you? Anyone else?
Yes.
Stuck. Okay. Let's see. Jackson's just coming in. All right. Let's take a look at it. Okay. So let's write down what you know that have to have a basis, right? And this is the set right here, right? So if we start with that assumption, we have to say, oh, our p vector is going to be some c1 times, let's call this v1. This is v2, because this is the set, right? This is v3. c1 v1 plus c2 v2 plus c3 v3. Okay. And now let's write it out. So P is 4 minus 2x plus 3x squared. And that has to equal C1 times V1, which is just 2. And then plus C2 times V2, and V2 is just minus 4x. And then plus C3 times V3, which is 5x, come on computer, x squared minus 1. Now let's write it all, let's expand a little bit here. So 2c1 minus 4 c2x plus 5c3x squared minus c3. Yeah? So with me so far, yeah? Okay, and that's over here equal to 4 minus 2x plus 3x squared. Okay, so these guys here, now this equation is really 3 equations because every coefficient of x, of an exponent of x. So if you go like, there's x to the 0, there's coefficients of x to the 1, and there's coefficients of x squared in this, right? Each of those is independent, right? So we already know that. So we know that that this 4 has to be equal to this thing, because there's no other, oh, well, sorry. No, the 4 has to be equal to this minus this, right? So we can take this apart. Let's take it apart. So the coefficients of x to the 0, okay, those are 4 on this side, and on this side, 2c1, my computer is being slow, come on, 2c1 minus c3, yeah? The coefficients of x to the 1 are minus 2 on one side, and on the other side, it's minus 4 c2. And immediately that gives me c2 is a half. So that's nice. And then the coefficients of x squared. On one side, it's 3. On the other side, it's 5c3. And this gives me that c3 is 3/5. Yeah? And now I can plug it all in here to get C1. So I get 4 is equal to 2C1 minus 3/5, right? Now pulling it over, I'm going to have 2C1 is equal to, what is it, 23/5, right, guys? That seem right? So C1 is 23/10, which of course is just 2.3. Yeah. So do you see how this works? So the fact that the bases, remember, so one thing you may have forgotten is that if you look at the standard bases up here, this guy, like those are all linearly independent. They have to be a basis for one thing. And you already know that coefficient, that, powers of x are independent, right? So you already know that. And so over here, they're just slightly different, right? So these are 3 linearly independent vectors, right? These polynomials, but they're linearly independent, and you can tell because this one doesn't have any coefficients of x, right? So that it has to be linearly independent of both of these. This one has an x in it, right? But not an x squared, and it doesn't have anything x to the 0, so it has to be linearly independent of the other two. This one has an x squared, so it has to be linearly independent of these other two, right? So it's pretty easy to just look at that and show that it's linearly independent. Yeah? Okay. And then you're just using your knowledge of the fact that these powers are linearly independent to solve. And so now the coordinate vector for this thing, so P, so remember, and I'm saying C here, right? That's true, but really, you know, think about it, right? If you wanted to write a representation for P in this form, right? It is with respect to the standard basis, right? It's always with respect to the standard basis. This, like, kind of like when we're writing vectors in R3, where, you know, when you write a vector is 2 along the x and 3 along the y and 5 along the z, right? You mean with respect to the standard basis. Okay. So when you write this polynomial in terms of this, like this is going to be the coefficient of x to the 0, this is going to be the coefficient of x to the 1, this is going to be the coefficient of x squared, right? You mean with respect to this basis here, this one, the standard, okay? Whereas this is a different basis, and so if I were going to write P now in that basis, I'd have to write it like this, right? I have to write, oh, it's, where's C1? 2.3 along this vector. It's, what is C2? 1/2. 1/2 along this vector. And it's 3/5 along the other vector. And let's see if that works, right? So let's do it. So what we're going to do is we're going to actually do this linear combination. So I'm going to say P is equal to 2.3 times the first thing, which is 2, times 2, plus, you know, 1/2 times the next thing, which is 4x, and then plus 3/5 times the last one, which is 5x squared minus 1. Right? Let's work it out. So this is going to be, you know, 4.6, and then minus 2x, and then plus 3x squared. Looking good so far. Minus 3/5. So now 4.6 minus 3/5. Okay, so I have to think about that. So 4.6. What is this in fractions? Somebody quickly.
4 3/5.
4 3/5. Okay.
It's just 4.
Yeah, it's just 4. Thank you. There you go. Right? Because it's just 4. It's 4 3/5. Okay, great. Okay, so 4 minus 2x plus 3x squared minus, 3x squared. Yeah? That's P, isn't it? Yeah? So we just, writing it like this tells us what the components are with respect to this basis. Yeah? And again, we can do this with MATLAB as well, right? So let me, I gotta stop the share and share it again with the whole screen. Give me a second. So I made the matrix A. So if we go look at A, there, right? Because what am I doing? Let me annotate here, give me a sec. Come on, stupid Zoom, what's your problem? Zoom, you're making me crazy. It like hides the annotate, there it is, okay. You ready? Okay, so because remember, right, we had our basis was, you know, basis vector set was, I don't remember what I call it now, okay, whatever. The set was 2, right? And then it was minus 4x, and then it was 5x squared minus 1. So to put that into a matrix form, right? Where remember, it's always you put the vector. So think of the vector. So let's write this again as a set of vectors. So V1, let's write this. It's with respect to the standard basis, this would be 2, 0, 0, right? Because it doesn't have any, because this is the coefficient of x to the 0. This is the coefficient of x to the 1. This is the coefficient of x to squared. V2 would be 0, 0, minus 4, 0. And V3 would be, minus 1, 0, 5. Yeah, everybody get that? And so when you put it in a matrix form, remember you put down, right? So 2, 0, 0, 0 minus 4, 0, minus 1, 0, 5. Okay, and then I put in my x vector as well. So x is 4 minus 2, 3, because it was 4 minus 2x plus 3x squared. That was my p, right? Or x. I'm calling it x here, but you could have called it p. That's our p, right? Or x equal p. Okay, so I put that in here as 4 minus 2, 3, right? That's the coefficient of x to the 0. That's the coefficient of x to the 1. And that's the coefficient of x squared. Yeah. Okay, and then I did my answer, C's, are the inverse of A matrix multiplied with the transpose of X, because it has to be a column vector, right? Because the transpose takes a row vector and puts it into a column, okay? And what did I get? What do I get? When I get that, I get C, C1 is 2.3. What do we get for C1? Yeah, 2.3. We got 2.3. 0.5 and 0.6, right? 0.6 is obviously 3/5. Yeah? Any questions on this? People got stuck because it looked a little different, huh?
Yeah, I was setting 3x squared equal to C3 times 5x squared minus 1 without doing the,
Oh, yeah. You got to split it into its, powers
yeah,
of X, just like you would normally do. That's the thing. Like if I gave you the equation, if we go back to the screen here, if I gave you, I'm sorry, I got it. This thing is like an idiot. I'm sorry. If I gave you I forgot that it does that. God, why are you so dumb? Nobody wants you to do that. Let me move it over. There we go. Okay. So if I just gave you this equation here to solve, right? You would you would gather powers of X, right? I mean, that's what you would do. Like you just normally would do that.
yeah,
So it's kind of like the components of the vector, right? The X, Y, or Z component, they're independent. So you gotta, solve, it gives you 3 equations. Kind of like Newton's equation, F equals ma. It gives you 3 separate equations, right? That's because the X and Y components are independent.
Yeah.
They're all with respect to independent bases is what I mean. All right, let me erase this. I forgot I could clear that. Okay. Okay. All right, well, let's move on. We are going to talk now about inner product spaces. So we talked about how, we have vector space, right? And then vector spaces come with addition and they come with scalar multiplication, right? You got to define those or you can't even talk about it because you can't test the vector space tenants, right? You can't test if it's closed under addition. You can't test if it's closed under scalar multiplication. You can't test that unless you have an addition and a scalar multiplication. Okay, but you don't have anything that allows you to, do anything with 2 vectors except for add. You can't do anything but add to 2 vectors, really, right? There's no dot product thing that we know from R3. So the vector space that I keep talking about, R3, where it's like the vectors, the 115 vectors, right? Yeah, they're the 115 vectors, but I have never said that there was anything called a dot product, right? So in that R3 vector space, there is no dot product. Okay, the dot product you know and love from physics doesn't exist until you define it. You define that particular, you define a dot product, and we're going to see it doesn't have to be the dot product you all know and love, right? Just like plus doesn't have to be the plus that you all know and love. Could be something else, right? As long as it works and doesn't, mess up your space. So what we do is we say we impose an inner product space on a vector space, okay? So, and there's an inner product space that you all know and love, and that's the usual dot product, right? That you've done a billion times in physics. But it has a bunch of properties that you probably never thought about, because to be an inner product space, it has to adhere to a bunch of properties. So let's take a look. So here is my my theorem to remember, right, page. And you can see that we have a bunch of things. It's only 4 actually, which is nicer than 10, that's for sure, for inner product spaces. Let's read the definition. Suppose U and V and W are all vectors in a vector space V. Ignore the fact that V doesn't have a thing over it. That was my bad when I was making this, because sometimes vectors are signified with bold. So anyway, sorry. These are all vectors in a vector space V, any vector space. And C is any scalar, okay? An inner product on the vector space is a function that associates with each pair of vectors in V, say U and V, a real number denoted by this weird bracket U, V, weird bracket, right? That satisfies the following axioms. 1, it is, it's commutative. So even though it has little brackets, we usually say U dot V, even though we don't mean necessarily the dot product you know and love. It might be different. Or some people say U inner product V, right? So I'll probably interchangeably use those. So U dot V is equal to V dot U. That has to be true. U plus V dotted with W has to be distributive, right? In this way, it has to be U dot W plus V dot W, right? They have to be able to distribute that way. Scalar C needs to be able to be pulled out of the dot product without any problem. So the dot product of C times U on V has to be C times the dot product of UV. And 4, U dot U is greater than or equal to 0, right? Always. With U dot U equals 0 if and only if U is 0. Okay, that's an important one. So U dot U with it dotted with itself has to be greater than 0. No other ones, you can have a negative dot product as long as the two vectors are different vectors. Okay, and you can only have the dot product be 0 between U and U if U itself is 0. These are very, very important. A vector space along with an inner product is called an inner product space. Okay, so now you've got the vector space and the inner product, and then those two things become the inner product space. We often talk about the norm of a vector, the length, and I'm going to put that in quotes, the length, because for spaces like polynomials, function vector spaces, right, matrix vector spaces, that the length is not going to be the length that you think of, because the length that you think of in the inner product space that we use in 115. So that inner product space we use in 115 is the usual one with the regular old 115 vectors and their plus and their scalar multiply, along with the regular old dot product you know and love, right? That is the inner product space that we use in physics 115. So that when you take the length of a vector, it's pretty clear. It's literally the length of the vector, right? In whatever units, right? That length might be, 10 newtons if it's a force, or 3 meters per second if it's a velocity vector, right? So it's represented on paper as literally a length of a vector, right? So, but if you now have it a different space with a different inner product, length is going to be a little abstract. Okay, so this is down here at the bottom. It says definition. Suppose that V is an inner product space, because that means a vector space V with an inner product. The norm or length of a vector U in V is defined to be with these two vertical lines, U dot U to the 1/2, meaning square root of U dot U, which is what you've done a billion times in physics, right? Between two vectors, or I'm sorry, to get a length of a vector. That's what you've done. You may not realize you've done that, but that's what you're doing. Don't worry about this Cauchy inequality thing. But this prescription is used as the norm or length, and again, length is in quotes, for lots of vector spaces with lots of inner product spaces, which could be based on vector spaces of polynomials or functions or matrices or whatever, right? But that same procedure is used. So once you have an inner product space, you can define something that people call the norm or the length, right? Norm is more general because it makes people not think about actual length of a vector, right? Anyway, okay, so let's take a look at the regular old dot product that we have in, like, you know, R3 or R2, okay, that you know and love from physics. All right, so let's say we have two vectors, and we're going to go in R2 with V being regular Phys 115 vectors. Okay. And let's say we have two of those. We have U is equal to, you know, U1, U2, and V is equal to V1. Oh, sorry, no, it's component V2, right? Then the prescription for the using the inner product space that we know and love from physics of U dot V, right? And you know this as U dot V, right? That the dot product is U1 V1 plus U2 V2, right? Yeah. You multiply the components together, like these would be the two X components, let's say, if these were the standard basis, and these would be the two Y components multiplied together. You all know that. We also use that we also make this notation UI VI, which is meant to say that you sum over the i's, right? So these repeated indices are summed over. It's kind of a shorthand for sum over all the indices. So for instance, let's take R4, right? So now we have four-dimensional space, not space-time, but space, and use the V's being regular Phys 115 vectors, but now in 4 space, meaning that they just have 4 components, X, Y, Z, and I don't know, something, W, okay? Physics 115 vectors, and if the inner product space is this inner product, then that would just be, you know, if we have a vector like U, it would be U1, U2, U3, U4, and V, of course, would be V1, V2, V3, and V4, 4 components, right? X, Y, Z, and W, let's say. And then the inner product, if it was the regular old inner product, like the same kind of inner product as we have in 2 space or 3 space, it would just be U1, V1 plus U2, V2 plus U3, V3 plus U4, V4, right? So the shorthand is nice because you can just be like, oh yeah, it's U1, UI, VI. And I put the indices, the indice up usually just signifies, hey, sum over these two, but it could be down as well. Because, you know, if you now all of a sudden wanted to work in like 24 dimensions, you don't have to write them all out like this, or you just write it like this, right? That makes sense? But this is a particular inner product that we use in 115, right? It's not the only inner product that you could put on the vector space that you all know and love from 115. It's not the only one. You could put other ones in, right? So for instance, let's suppose we have the usual vectors in let's say R2. So we'll go back to R2 with Phys 115 vectors is our vector space. So that's our vector space V, a capital V, right? We could have an inner product. So suppose we have a set of numbers, W. They're just numbers. You know, I equal 1 to 2, 1 and 2, right? That are real. And positive. So let's take an example of W 1 equals 2 and W2 equals 3, okay? We could define an inner product such that, okay, define inner product, sorry. Where we have two vectors in, let's say 2 vectors in our space in V, U and V, little v, sorry. The inner product between U and V defined as, W1, U1 times V1 plus W2, U2, V2. Okay? And in fact, that is a perfectly good inner product, right? So, right? So you have to multiply the x, when you take the two x components and multiply them together, you got to multiply by 2 because that's what W1 is. Then you take the two y components, you got to multiply by 3. That's a perfectly good inner product. And I would like you to think about the axioms. I'll put them back up. And think about this inner product, and are there any of these axioms that this inner product doesn't work for? So think about it for the next few minutes because class is almost over, and we'll go over it when we come back. Think if you can find one that it busts.
So any real and positive.
Yeah,
W?
but in this case, I actually said it was 2 and 3, so you can use 2 and 3 if you want. But yeah, any two positive.
Are we trying to find a W that doesn't work?
Well, no, you can stick with these two. I want you to see if it works for all of these. If it's true, if this inner product, because this inner product says for any two vectors U and V, this is what you have to do. You have to multiply, the two x components by W1, and then add, the two y components multiplied together times W2. Right? That's what it says. It's the prescription for that inner product. See if that violates any of these axioms so that maybe it's not an inner product.
Be if U and V are different dimensions?
You have to specify V, which we did already. V
Okay.
is R2 with usual physics 115 vectors in R2. Right? That's the inner product space is the vector space plus an inner product. Right? So I'm saying this is the inner product, but the vector space is the usual R2 with physics 115 vectors. So you just need to go through those axioms and see if you can figure out if one of them is not going to work anymore because of my definition of a dot product. Or maybe more than one will work. All right, guys, class officially over. I am stopping to share. So tell me when we come back on Monday whether this is really a good inner product space or not, or does that inner product that I defined defy one or more of these axioms, okay? All right, guys, I am going to stop the recording.